first talk is by Tim Johnson, who has put together some Foodweb perspectives with Lars Rudström.
Thank you, Alistair. So again, as you see with the slide here, lots of colorful cast of characters contributing to this, lots of different time series drawn together to try to sort of pull in this Foodweb perspective. So the simplified Foodweb for Lake Ontario, we basically are looking at a system as with all of the Great Lakes. Basically phytoplankton, algae is what's feeding the zooplankton. Zooplankton, benthic invertebrates is what's feeding our prey fish, which we've heard some about and we'll hear more about in a moment, and that's supporting these both economically and ecologically important top predators in the system. And so last year, this was the second to last slide that I used, trying to convince everyone in the room that understanding lower trophic levels is important to understanding healthy fisheries. One, it gives us an opportunity to engage a broader public when we're thinking about things like water quality issues and so on, when we think about other user groups besides just anglers, that the lower trophic level helps people embrace that. But it also allows fisheries managers to anticipate and plan and adapt to the changes that are going on in the system with a little bit more foresight by understanding what's basically feeding the production that's ultimately supporting the fisheries. And so the ecological change that's going on out there, these adaptations that we want to have some foresight on, there's many of them out there: invasive species, changing in nutrient status, initially eutrophication, now oligotrophication, chemical pollution, watershed development, and so forth. But really, ecological change is nothing new out there, and so why is it that we need to suddenly embrace it? These are just a series of different data for Lake Ontario, fluctuations in water levels at the top, average lake temperature, ice cover, and then even changes in this case, commercial fisheries, both composition and production. So change is going on out there, but by embracing a more holistic understanding of the ecosystem, I think all of us in the science and management community will be in a better position to manage for changes that are happening, or basically to understand the uncertainty that's out there. Basically how these ecosystem changes are affecting the quantity and quality of these fisheries, and therefore how do we couple the lower trophic level changes with fish production. So some of the time series, starting off at the bottom of the Foodweb with nutrients, a long time series here spanning over 40 years. When we look at it over that whole trend, we see a very dramatic decline from the early 70s down to the present state. We're currently sitting a little bit below the Great Lakes Water Quality Agreement target of 10 micrograms per liter, but really for the last 20 years or so, well, there's some fluctuation. There really hasn't been any significant decline in the nutrient status. Similarly with chlorophyll A, so this being an index for sort of phytoplankton or our algal community that's out there. Again, lots of variability earlier on in the time series, but again, since about the mid-90s, lots of variation, but no real trend going on here. Zooplankton, so these are the small animals that are ultimately feeding the baby fish out there and feeding our small prey fishes. Again, when we look over these long time trends, we see significant declines. This is a composite made up of an historic offshore time series that DFO started in the early 80s, and more recently the U.S. biomonitoring program that's done by a collection of the U.S. agencies. And so when we look at this, we see very significant decline that went on through the time series. We see a significant change in the composition of the community, the loss of these cyclopoids, and really in what we're seeing now, much lower levels. And so as Steve and Andy sit here keenly paying attention, I guess the question is, are we really on a trajectory for catastrophe? I guess may as well just jump to last year's closing slide, which said, okay, so for all this change that's going on out here, declines, somehow we continue to support very productive fisheries. And so what I want to talk to you a little bit about today in this Foodweb perspectives is sort of trying to decouple this, trying to give you some explanation for how we can have these dramatic changes at the base of the Foodweb and somehow we continue to sustain very strong productive fisheries. And the theme of this discussion is going to be about spatial complexity. The two graphs that I'm showing you here, the upper one, this is satellite imagery of basically a surrogate for chlorophyll A, the outline of Lake Ontario here, concentrations, the redder colors are higher concentrations through greens to low concentrations in the blue. So clearly there's a tremendous amount of spatial variability, more of the production of chlorophyll happening in the near shore than offshore, but when you look at any one area, there are nearshore areas that are low, and there are offshore areas that are high. This lower panel here is an echogram of pelagic preyfish from hydroacoustics, and again we see a significant amount of spatial variability, this being the north shore, this is the south shore of the lake, this is the north shore of the lake, the thermocline running across about here, and the majority of our fishes sitting below the thermocline, but again, very high concentrations, mid-lake, very low concentrations, in this case the north shore, and modest concentrations south shore. So there's a tremendous amount of spatial variability that goes on in the system, and this was really the objective of the 2013 CSMI, was to try to understand how spatial variability was feeding into our understanding and providing insight into the uncertainty. Sorry, I panicked here because I saw the red light come on and say I'm done, but I hope I'm not. So anyway, a little bit of context here. So thinking about nutrients and what's going on. So this special publication came out in the Journal of Great Lakes in 2012, looking at nutrients. So everyone stops panicking. This is a Lake Erie image, but this is cladophora in the eastern basin of Lake Erie. But really the conclusion for nutrients and how it ties into space is the fact that the tributaries are a huge influence to the coastal processes. This effect extends up to 4 kilometers offshore. The tributary load was over 3 times that of everything coming out of the wastewater treatment plant. So back in the 70s, we were dealing with point source pollution. Now we're dealing with non-point source pollution. But when you think about nutrients, I showed you a graph that suggested that we were down at much lower levels. That was reflecting on the offshore. The goal is 10 micrograms per liter. We're not that far off. We're more than an order of magnitude more phosphorus in the near shore. So there's a huge amount of nutrient out there. So when people start to ask the questions to say, are these problems, can they be managed by adding more nutrient? The reality is you add more nutrient, that's what you're going to end up with. So nutrients is not a solution to the problem right now. Big change in the system out there is transparency. We measure this with a Secchi disc. This is looking how far down the water the clarity is, and a significant trend upwards. And so the lake is basically getting clearer as time is going by, and that trend seems to be capping out a little bit now, not a tremendous amount of change in the last 10 to 15 years, but the lake is substantially clearer than it was certainly 30 and 40 years ago. So a hypothesis I'll explore with you today is whether this increasing transparency is allowing the light to penetrate further into the water column, increasing the production of the phytoplankton of this algae at greater depths, and that's also going to stimulate the production of cold water zooplankton down deep. And so basically, is it that we're simply needing to look in different places as the lake is fundamentally becoming a different system, that the production is out there, but the production is occurring in different locations than it was when we started these time series. And so an important concept to embrace here is something that's referred to as the deep chlorophyll layer. And this is simply a graph showing temperature here as a red line. So when we talk about a lake, we talk about this warm upper layer, the epilimnion. We talk about this zone of transition, which is the metalimnion, and then this constant cold water, which is a hypolimnion. And this deep chlorophyll layer is the fact that we see a peak, a maximum in the chlorophyll production below the thermocline. And that is an event that, or a phenomena that's been occurring with greater frequency at greater depths. So this is some data provided by Brian Weidel and others showing a time series of the depth of maximum chlorophyll recorded through a series of long-term monitoring programs starting in the 70s. But back in the early days, the depth of maximum chlorophyll was about 5 to 10 meters below the surface. Now we're in a case where it's 15 to 20 meters below the surface. So the depth of maximum production is occurring much deeper in the water column. That was investigated in 2013 using a variety of systems. This is showing a glider that was used, a partnership between NOAA and GLOS and the USGS and some people at Cornell. And basically this is an autonomous submarine that cruised around out in Lake Ontario, following this track, bobbing around, and it was basically recording a whole variety of parameters out there. And this is basically a graph showing the density of peak chlorophyll occurring again at a depth corresponding here to about 20 meters as you look down into the water column. Lots of other systems were used in 2013. Earlier in the day, if you were listening here for Paris Collingsworth's talking about a tri-axis, which is a system the USGS has. We've used an optical plankton counter, DFO, used that system, and so again, we're just showing that the depth of chlorophyll, in this case for a transect across the far western end of Lake Ontario, was occurring at greater depth. And now if you map that onto things like zooplankton, certainly where we see the chlorophyll occurring at depth, we're also seeing the peak in zooplankton occurring at depth, and this just for different strata. So we're now saying that the production is possibly occurring at greater depth. It's occurring in different locations than it was historically. Another element to consider in this case is understanding the movement patterns, the day-night differences for active biota, in this case zooplankton. So if we look during the daytime at 3 different stations, basically sort of off the mouth of the Niagara River, during the day there's very little zooplankton biomass in that warm upper strata, and more of it's occurring in this metalimnion, in the mixing layer, or even down deep. But when we look at these same stations and the same dates at night, we see a totally different phenomenon. At night, all of the biomass moves up into the warmer strata, and the communities are basically shifting. So understanding how things are changing both in space and time is important for us to understand what the overall productive capacity in linking these lower trophic levels to higher trophic levels. So if we go back and revisit our zooplankton time series, this is the original one I showed you going down, representing just the epilimnion, just the upper warm strata. This is a shorter time series, but it's as long as we have available for the whole water column. And so, while there is a downward trend, really when we look at the zooplankton over the last decade, there has been very little change. There has been a shift in the community, a loss of the cyclopoids, and more calanoids now. And last year I talked about how that's a complex relationship between the presence of Bithotrephes, the invasive predatory zooplankton, alewife, and the cyclopoid community. So there's complex food web dynamics that are driving some of these things. So again, I alluded to this earlier. This is a prey fish distribution in echogram, the thermocline occurring right here, and the concentration of fish below it. So again, the prey fish are varying in space and in time. This is some data from graduate student James Mumby working up some of the data from 2013. And the question here is really, are all the prey fish created equally? And so this upper panel here is stable isotope data, nitrogen reflecting sort of the trophic position, so things eating lower in the food web versus things eating higher in the food web, and carbon reflecting the difference between sort of near shore sources versus offshore sources. So we see our 2 sculpin species up here. We've got our rainbow smelt in the middle. We've got our gobies to the side and our alewife. So the species of prey fish are different in the sense of where they draw their energy sources, but also where they fit into the food web. And so what James has tried to do is to look at Lake Ontario by breaking it into 4 quadrants and looking at how these species also vary in terms of the location amongst quadrants, amongst seasons, spring, summer, and fall, and amongst sizes of these fish. And so in this matrix at the bottom here where the word yes appears, it's saying that there are significant effects through a general linear model. So for alewife, not all alewife are created equally. They vary significantly by location, by season, and by size for both carbon and nitrogen isotopes. For smelt, the variation exists primarily by location and size without a seasonal effect, and for nitrogen, it only exists for size. Gobies, a similar pattern to the smelt, that there's a location and a size effect. But for our sculpins, the only significant effects that are showing up are for nitrogen. So again, all these prey fish are not created equally in the lake. So when we think about these spatial patterns, what's happening with nutrients is translating into algae, is translating into zooplankton, and it's also affecting ultimately the chemical composition, the health and well-being of our prey fishes. Predators now, this is isotope data for our predators. Similar pattern, nitrogen and carbon, and this is just for a series of different fishes, and again the relative size and the orientation of the signatures showing that the predators are different. And so we're now tackling that through a new project funded by the Great Lakes Fisheries Commission using some data storage tags. So these are basically big computers that are attached to a fish. The fish swims around. These are programmed to pop off about a year later. We recover the tags and we download the data in patterns like this. The data I'm showing you here, we put these tags on fish in the spring of last year and some in the fall of last year. One fish that was tagged in Port Credit in the end of September was caught by an angler 3 weeks later at the Salmon River. That's a minimum linear distance of 270 kilometers. Right away, I don't think that's how many of us thought that a rainbow trout behaves. It boogies from one end of the lake to the other, and this is simply 6 days of its life. What we start to see, this is recorded at 1 minute time intervals. At night, the fish tend to sit at a constant depth, and during the day, they go through very dynamic behaviors. At night, during the day, at night, during the day. We can now start to analyze this information to understand the behavior of the predators and how the predators map onto the different prey, and collectively through that, hopefully we'll get a better understanding about how the spatial distribution of energy sources, nutrient sources, and lower trophic levels is ultimately feeding into decisions around fishes. So that'll all be encapsulated in things like this topography map showing a more complex understanding of the food web for Lake Ontario. And again, revisiting this, I think it is important to understand lower trophic levels, to understand and manage fisheries, and ultimately for Steve and for Andy, hopefully there won't be any surprises, and so when Andy thinks of lower trophic levels is this jack in the box that's just waiting to pop up, and Steve's waiting for the answer, that hopefully we won't go there. So, thank you.